some examples now? Okay. So here, let's say we have this. So let's say a race occurs and there's 8 people running 1 mile. And with the race, the one who finishes first gets the gold medal. The one who finishes second gets a silver medal. And whoever finishes third gets the bronze medal. Okay, so the question is, how many ways can these 3 medals be awarded? Well, of course, repetition's not allowed, right? You can't give more than 1 medal to someone. You know, we know there's 8 people running, so you can't give more than 1 medal to anyone. And the order does matter. You know, whoever finishes first gets the gold. Whoever finishes second gets the silver. So in this case, we have permutations. So order matters, no repetition. We have P of 8, 3 here. I mean, you could use the formal definition, the 8 factorial over 8 minus 3 factorial, which turns out to be all this. It's actually 8 factorial over 5 factorial, which is 8 times 7 times 6. Let me just show you in Desmos, though, because I think Desmos might make it a little bit easier. And let me share that, though. Graphing scientific. Okay. So again, we have 8, 3. So it's NPR. Permutations, that is. So we click on functions. Right. Then we go to NPR. We have 8. Let me see if I can do this. 8, then a comma, 3. What's the close parentheses? Ah, here it is. Down here, you close it, press enter, and you get 336. You know, it's the same thing as 8 times 7 times 6, 336. So there's 336 ways we can give away those 3 medals. On the slide, I don't know if I hope you have in front of you, I did email it. The next part is, what if instead of 8, there were 10 people, though? It's the same question, essentially, except instead of 8 people running, there's 10. In that case, it's still NPR. Right? The only thing different now is that there's 10 people instead of 8. So it'd be 10. Wait, let me go back to this. You know, let me do it this way. 10, comma, 3, close parentheses, 720 in this case. So in this case, there'd be 720 ways in the second part of the question, because they're saying there are 10 people there. Okay. All right, are there any questions on that? Okay. All right, so that's what happens here. So we did this one as well. Okay. Okay, so that's this question. Let's do another one. In this one, we want to know how many ways can a 4-person executive committee with these 4 offices, I guess. How many ways can a 4-person committee be selected among 16-member board of directors of a nonprofit organization? So in other words, we have 16 people and we want to choose this committee of 4 people. Well, of course, no one can hold a position, more than one position, right? You can't have someone who's a president and a vice president. So no repetition. Not only that, the order in which you choose people matters. You know, the first person chosen is going to be president, I'm guessing. The next person chosen will be something else. Then the third person will be something else, and so on. So in other words, order also matters. That's how elections generally are. So no repetition and order, we have permutations. So there's 16 people, and you're choosing 4 of them. So you would have P of 16 comma 4. And if you do that in Desmos, this is what you would end up typing, just like I did before, actually. And you would end up getting this amount. I mean, this is the calculation with factorials, but you could just use Desmos if you want, and you would get this. All right. Okay, that's good. Now let's calculate some probabilities. I mean, here we were just determining how many outcomes there were. We can use this to determine the number of outcomes, hence we can determine probability. For instance, suppose we're making a 4-digit password, okay? And we're going to use any of these 10 digits. So we're making these passwords now, 4 digits. If we choose a password at random, what's the probability of choosing one that has no repeated digits? That's what we want to know. Well, what would the sample space here, right? For probability, you want to know the total number of possible outcomes. It would be all possible 4-digit passwords you can make. Well, how many are there? Well, for any 4-digit password, you can have repetition. You can have repetition and no repetition. In other words, repetition is allowed. And there are 10 digits for each digit. You know, there's 10 numbers for each digit. So by the counting principle, what we saw before, you would have 10 to the 4th. Okay, maybe this will help. Right? Just like what we saw before, we have, for a 4-digit password, you have 10 choices for each digit, right? You have 10 choices for the first, 10 possible ways of choosing the first one. So for the first category, so to say, the first digit, you have 10 choices. Same thing for the second digit, which you could think of as our second category, third, and fourth. And by the multiplication principle, you just multiply, which is 10 to the 4th. And you get 10,000 passwords. That's what you end up with. Now, how many passwords, though, are there then? So this is the total number of passwords. These are all of them, that including the repetition ones. But what about the ones that don't have repetition? Well, those are the permutations. That's P of 10 comma 4. But again, order matters. So the number of passwords we're interested in the permutations, the ones that have order, but they don't, but repetition doesn't matter. But we don't want repetition, excuse me. That's what this is. So the probability then of choosing a password with no repeated digits would be this. Right? This is our sample space. These are the outcomes we're interested in, or the outcome corresponding to our event. You know, the passwords with no repetition. So we have this. Are there any questions on this? Okay. For this one, I was going to have everyone try, but we have 5 minutes left, so let's just do it together. Here we're making a 6-digit password. Excuse me, a 6-character password where each of the letters A through Z could be used. So this one's a little bit different because now for each digit, so to say, we have 26 choices. And again, let's say we choose a password at random. What's the probability of choosing one where there's no repetition? In other words, just like before, what's the probability of choosing a permutation? Again, order matters because it's a password. Well, it's 6 characters long, right? So 1, 2, 3, 4, 5, 6. And again, any of the letters of the alphabet is a possible choice for each digit. So we have 26 choices for the first one, for the first digit, first letter, 26 choices for the second letter, right? And so on and so forth. 26, 26, 26, 26. Right? So for each letter, for each character of the password, we have 26 letters, 26 choices. So by the counting principle, there are 26 to the 6 possible passwords. But again, we want the probability of choosing a password that has no repetition. Again, order matters. So we're really looking for the probability of choosing a permutation. Well, how many permutations are there? That's what this P of 26, 6 is. Which is this. Right? Which is this. And that becomes this. And so the probability then is this number divided by this number, which turns out to be this. Okay. So that's what we're looking for. Okay. Are there any questions on this one? Okay. So here's something new. Not going to go too far with it today, but that's okay. Sometimes you're going to want to find the probability of something happening at least once. The probability of an event happening at least once. Now, you could get that directly, but there's another way to get it. If you remember, if we have an event, right, the probability of an event plus the probability of its complement is 1. Well, the complement of an event happening at least once is the event never happens. They're complements, you know. The event happening at least once, well, if that does not happen, so the event does not happen at least once, that's the same as saying it never happens. So using that, we have this formula. So this is actually useful because sometimes this can be tricky to get, the probability of an event happening at least once. But if we can get the probability that the event never happens, then we're good because we have this formula. All right, better stop now. We have like 5 seconds left. Okay.